Yeah, so I am recording it, and I will send you all a copy of the recording. And now let me just have a quick look at the questions. Unfortunately, I'm on my own here. I normally have someone else looking at the questions. Is it possible we get a recording? Yes, it is. I'll make sure you all get. How is a subatomic particle used in the quantum computer if it changes when it is observed? Oh, great question, Amanda. And the answer is, it doesn't. It dies a death. If it's been observed or measured, you may as well throw the whole computer out. I mean, you know, they reinitial it and start again. But a quantum computer can only work with when the subatomic particle is in superposition. And I will explain almost right now about superposition. So let's go through, and thank you for asking the questions as we go, because I like that. I'm happy to stop and answer questions. And if I don't see the questions, please forgive me. Look, this is a teleportation slide. I always like to show this because being developed for good purposes. I'll read out the questions in case you can't see them, but Amanda's asking, is quantum computing being developed for good purposes? And the answer to that is hopefully yes, but there's an underlying worry, and governments are looking into that now, that it could be used for bad purposes like the dark web. And what we should understand is that with quantum computing, for the first time ever, we're going to have an unhackable code. So you're going to be able to send messages which can't be hacked and never ever will be. Now you might think, oh, that's not that big a deal. That is a huge deal, because we have the dark web at the moment and lots of scurrilous information goes on there. But to be honest, it's the best thing that's ever happened for the law enforcement, because we can find and then we can, you know, copy and paste and see what these people are up to. When the dark web type people get hold of a quantum computer, and there's a protocol, write this down. Quite often I'll say, write this down, and it'll just be a small phase, but it's the BB84 protocol. BB84, and that's gonna change the world. But here, this is I like to do this because it's so exciting talking about. This is a picture, a diagram of teleportation, one human moving in time and in distance immediately. And I'm going to ask you all a question. You can type the answer in the chat if you would. But quantum scientists are talking about, imagine putting a subatomic particle on your hand, which you can't, but you know what I mean. Imagine a speck of dust, and then imagine going boom, and that speck of dust traveling 150,000 kilometers into space, into an orbiting spacecraft. So you've got a particle of matter automatically going from the Earth to an orbiting spacecraft. And I like to ask, when do you think this will be possible? Do you think in 20 years' time, in 30, 50, 100 years' time, or we'll never be able to do that? And when I say a piece of matter, I mean that actual piece of matter. Who's that? Who's that ruining my presentation? Amanda, yes, it's already been done, and Joanne as well. Yes, everybody wants to ruin my little bit of fun. Yes, it's already been done. Now, isn't that amazing? This is what you should be telling your friends, and over your next barbecue, talking about how can a piece of matter go from, you know, the Earth to an orbiting spacecraft. They went from a laboratory in Tibet to the Messias orbiting spacecraft, and it's been done many times since then. Yeah, you'd be surprised. Amanda's saying, you know, it goes over their heads from there, and obviously it does. But you know, I do like this as a not just a workshop, but as a course. And at the end of that course, you'll be able to understand what's actually happening in teleportation. The actual process is not that difficult. You're just using a few quantum gates. In fact, we're going to go close to solving that tonight. Yes, thank you, Ara. I hope I'm pronouncing your name properly. But yes, it went to the satellite Nicias up in space. So it's amazing. And we've now started doing groups of subatomic particles and entangled particles. And that's all very, very exciting, because at some stage we'll be able to do atoms, and it's all you know, it's amazing because one can think, well, if I sent Amanda and got all of Amanda's atoms and teleported them, would her consciousness be there? Would her memories? Or you know, so it's all very interesting. My God, this is just slide one. We're going to take hours and hours. Fantastic. Thank you for those questions. Now, look, I love this statement. I never listen to wealthy people. Let me give you the tip. They don't impress me. Scientific people impress me. But Jeff Bezos is obviously no fool, and he's the founder of Amazon. And he said just a few months back, quantum computing is the future. I am not exaggerating when I say it will change everything. And I like that, because it will change everything. In fact, try not to think of it as computing, because then you start narrowing your focus on what computing is. And the reality is that it's going to do so much more than that. Quantum sensing, understanding things we've never understood before. We're already understanding bird migration, photosynthesis. These are all quantum effects. They could never be anything else. I also want to just quickly mention that Australia is getting very big into this. Is there quantum effects in AI yet? Definitely. People are now talking QAI. In a few years, you will not have AI on a normal classical computer, the fastest computer we have today. Yeah, so it's all QAI now, and machine learning. I'm involved with a few projects that are very heavily into that. So yeah, definitely that's the future. Is that worrying to you for the human beings? No, not really. I think all technology, let's face it, since the beginning of time, when we've started doing technology, it could always be used for good and bad. You know, like obviously nuclear fusion springs to mind, you know. So let's just hope that it's going to be used properly. We're aware of the issue. But CSIRO are talking about in 10 to 15 years, the industry, you know, employing 16,000 jobs with millions, billions of dollars in income. Hello, Anne. It's Anne from the CSIRO, who I do some work for out there with Pawsey. Anne, lovely to see you. We've just started. Right. And also there was, on the left, you can see our leader, our supreme being. Yeah, the wheel took jobs away. Well said, Joanne. Yeah, I believe it changes jobs. I mean, we wouldn't have a motor industry without the wheel. On the left there, we've got Scott Morrison, and he just in November said that he's putting a lot of money into quantum computing, basically. So everybody's really understanding the importance of quantum computing. Nice to see you, Anne. Lovely to see you. Okay, so today I'm going to give you some fun facts, and they will be fun, but they'll be amazing. So let me, I'll go through them. And then there's going to be two sessions. Basically, I'll talk first about the mysteries of quantum physics. Quantum computing is merely the implementation of the crazy quantum physics into a computer. So you need to know what's happening at a quantum physics level, and it's exceptionally interesting. Most people, or a lot of people, love to see this side of the presentation or workshop more than the computer side, because nature is quantum. What you have to understand is that you're a quantum being, everything is quantum, and it's very, very weird. When scientists, and quantum just means anything smaller than an atom. So when scientists first developed the technology to look into an atom, they were absolutely amazed at what forces were going on and how different it was. So there's this big, huge difference between microscopic, subatomic, quantum, and macroscopic, which is atoms and bigger atoms, molecules, and then eventually, you know, to us and the big system. So quantum effects only work at the quantum realm, and we don't know, it's very nebulous where that changes. And a lot of research is going into, is finding a point of demarcation, and, you know, maybe there isn't one. And then I'll talk about how it does computations, which is absolutely fascinating. How a quantum computer works, number one, is totally different from what we call classical computers. And by that, I mean the fastest computers on Earth today. And so when I say classical, I don't mean old. I mean everything else that's not quantum. I'll have some questions for you in the quiz, which will just be a bit of fun. And then we'll take a 5-minute break after each session. Now, the objective is that you leave more familiar and more comfortable with quantum computing, what it is, how it's going to affect you. And please, you know, keep the questions coming. And then what I'd like you to do, I normally ask, a lot of the time I am presenting to young teenagers, and I always say, go out and talk to someone about it. I mean, I don't mean go out and show off that you know something. Just go out to someone and, you know, do a presentation on PowerPoint for your, you know, aunts and uncles, for your family, for your next door neighbor, for your friends at school. And I always say the only way you're ever going to learn a topic or subject is lecturing in it, because when you do that, you naturally just understand the subject better. Right, so here's some of the facts I want to get over to you. Now, listen to this. The fastest classical digital supercomputer, which is an IBM one at Oak Ridge, it can perform 200 quadrillion operations per second. So this is nothing to do with quantum computing. This is a supercomputer. Isn't that absolutely amazing? 200, and I think it's 15 zeros. It's unbelievable. Then the question comes, Chinese scientists announced about a year ago now, the most powerful quantum computer in the world. It works 100 trillion times faster than that computer I was just extolling the virtues of. So that computer that does 200 quadrillion, it is estimated that our brains are capable of performing about 10,000 trillion calculations. Ara, thank you very much for that statistic. And Thank you for that, because there's a lot of quantum physics and quantum computing is changing everything, like Jeff Bezos said, and it is changing our knowledge of the brain. And, you know, then you've got your matrix type stuff. You've got your consciousness and supernatural type stuff. I may say, we don't know how quantum computers work. We don't know. Whereas with the classical digital computers, we do. It's merely a voltage is there or it isn't. But can you see how the digital computer is operating at the speed of light? It's unbelievable, 200 quadrillion operations a second, yet a quantum computer can work trillions of times faster. What the Chinese did, in 3 minutes, they did a calculation that would take that digital computer, the fastest one on Earth, and half the evolution of the solar system to do. Now, I may add that the question favored a quantum solution. So everything was in a favored quantum, and it's of no practical use. So no quantum computer has ever done anything practical at the moment. But that's going to change in the next 12 months. Oh, hello, Aditi. Lovely to see you. Oh, joy. I thought, yeah. Excellent. So, yeah, got all that covered. Isn't that amazing, though? I love that stat. And classical digital supercomputers, they use bits. Every computer on Earth uses bits, and it's either on or off. Quantum computers use what's called qubits. Now, when we have 300 pure qubits, and pure is a very important term here, we'll be able to reference, to map to the equivalent of every atom in the observable universe. So before we're talking about 20 quadrillion, we're now talking about figures that we will just never understand. It's unbelievable. And it does lead one towards thinking, where's all this headed? Okay. I use this often, so forgive me if I've asked you all this before, but it's very important to understand the difference between linear and exponential, which I'm sure a lot of you already know. But classical computers, the one with 200 quadrillion operations a second, actually is linear. Can't get away from that. All computers are linear, but quantum computing isn't. Now, if you have 10 people at a table, how many different place settings can you set? So it could be me opposite Aditi, or opposite Amanda, or Anne and Joe and Glenn, and we could swap everybody around. How many? So if you can put a quick answer in chat or shout out, I don't really care. Just 10 people around the table. Think of your Christmas placings. Is nobody going to have a guess?
Oh, might it be 10 to the power of 9 or 10 or something?
It's something very similar to that. Yes, it's actually, well, the answers, oh, here we go.
Yeah, that's it, 10 factorial.
Oh, 10 factorial. That's exactly right, Aditi. Yeah, so it's 10 times 9 times, yeah, 10 factorial. Thank you, Ara. So it's actually, and that actually equals, oh my God, I'm miles behind time-wise, but I don't mind that. It's actually 3.6 million. So when we talk about things like a vaccine, and the vaccine, thanks, Ara, the vaccines, well, all vaccines start in a computer simulation. If you've got a molecule with 10 electrons, it's all about sharing electrons. you've already got 3.6 million different possibilities. That's why it's so different. But with a quantum computer, we're going to be able to handle the likes of that. Okay. Your ATM card, again, I've done this with a few people, but when you use an ATM now, it's totally safe because it's encrypted with something called RSA, which is factorization. It's really safe. If you gave that transaction to someone, it would take them literally 300 million years to extract your PIN. But with a quantum computer, it will take 6 seconds. Now, notice I've put up a quantum computer FTQ. That means a fault tolerant. And that's like the pure one I mentioned before. And we're nowhere near there at the moment. At the moment, we're in, if you can write this down, NISQ, NISQ, which is noisy intermediate stage quantum computer. So what's happened is, I'll explain that when I get to the computation side, but it's important to understand that when we have fault tolerant quantum computers, we're going to be able to do things like this. And that gets back to Amanda's point before about, is it risky that someone could do something bad? And the reality is there is a risk. The delayed choice quantum eraser experiment, that's probably beyond what we're doing at the moment, but it's amazing. And it basically shows something very, very strange is happening at a subatomic level. And it indicates that events that have already occurred can be altered in the quantum realm. Noisy intermediate scale. I said something else. Yeah, you're right. Quantum era. Thank you, Aditi. Thank you for putting up the links, Aditi. That really helps. And then there's another question from, I think it was noisy. Yeah, that's exactly right. So we're in the NISQ era, and quantum developers are developing for the NISQ. Thank you, Ara, for, that's great, putting up a nice link there for everybody. So have a look at the chat, and that's a link on the delayed choice quantum eraser. On my channel, I have a number of presentations on the delayed choice. It's basically, we are going to talk about the double slit, hopefully, with but the delayed choice quantum eraser is like the double slit, but using entangled particles. Excuse me while I drink. Some more links. Thank you, everybody, for the links. That really does help. Okay, so now we're just starting to get into it. So look, I'll rush through this a little bit, but we'll handle it when we get the questions. So what is quantum computing? It's actually the manipulation of a subatomic particle while it's in this crazy state of superposition. So point 2, I'm going to explain superposition, and then quantum entanglement and quantum tunneling. Quantum tunneling, not so much, but quantum tunneling is worth knowing because it's like walking through walls at a quantum level. And it's actually the reason why our supercomputers are now never going to get any bigger, because they've reached the end of Moore's law, because quantum tunneling takes over and then everything goes array. So funnily enough, it's quantum that's bringing the demise of classical. Now, can you put in the chat if you, just tell me if you know, how many people here are aware of the double slit experiment? Unless we find a way to calculate with atoms, quite possibly. Okay, let me thank you, everybody. Excellent, yeah, and you poor Anne's had to listen to this presentation a few times. So look, let me, yes, thanks, Amanda. Okay, so look, this is the most important experiment, and it explains superposition. Oh, thank you, Anne. Yes, isn't that a lovely thing to say? Understanding more each time is exactly what we're trying to do. So thank you for that. Now look, the double slit is actually over 200 years old. It was first brought in by the handsome gentleman on the left, who's Professor Thomas. And what Professor Thomas did was I think I've got the name, I can't remember now. But
Young.
Ah, yes, Young. Thank you, whoever said that. Yeah, Thomas Young, thank you. So Professor Young actually wanted to find out whether light was a wave or a particle. Funnily enough, Newton was saying it was a particle. He called it a corpuscle. But anyway, Professor Thomas Young wanted to find out, conduct his own presentation. So back in 1801, what he actually did was got a little bit of sunlight. So he had the curtains drawn that there was only a slight ray coming through. And he aimed the ray at two detectors. The first one had two slits in it, and the second one registered the pattern at the back. So what happened to the light once it went through the two slits? Now, it's very important to understand, if you look at the first, imagine it being a wall with two big slits in it, and I had a machine gun and I'm firing up and down and across and to the side, you would expect the bullet holes in the back detector screen to be two vertical lines. Do we all understand that? I might be laboring the point, but it's important. And that's called a clump pattern. So if light was a particle, we'd expect to see a clump pattern mirroring roughly the dimensions of the two slits. Everybody okay? Now, if you imagine the same wall, but we have a room full of water and we're pushing the water through those two slits, what would happen is that the slits, the waves of water would interfere with each other. And in point of fact, you would get the same pattern that we can see on the detection screen on the right-hand side. So what we would get is multiple vertical lines with the most pronounced in the middle. Okay. So that's it, basically. So the beauty of the double slit, it's so easy to explain. So Professor Young did the experiment, and he saw an interference pattern like the one we can see here at the back detector screen. So he quite rightly deduced that, oh, light is a wave, and he's running around, everybody's congratulating him. And he's proven, basically, that it was a light. Now, that it was a wave, because only a wave would produce that interference pattern at the back detector. So for a whole 100 years, the whole Earth, the human society scientists, I once read that particle detectors can... yes, Ara, we probably have to talk about that off screen. With the delay, Ara is just saying there could be interference in the way we measure it. And we can, the delayed choice quantum eraser actually collapses the wave function and it doesn't do any measurement. So it's not the measurement that's producing it. Okay, we now move on just over 100 years in Einstein's Annus Miraculous, where he did 4 scientific papers. Most people just do 1 in a lifetime. He did 4 papers that have changed the way society is today. Unbelievable. And one of it was called, for which he got the Nobel Prize, was the photoelectric effect. And this is actually how solar panels work. So if you shine light on a metal, it will displace an electron. But it doesn't matter. You don't need to know what's happening. What you need to know is that it proves that light is made up of particles, because they increased the light and did make, no matter what they did, it still came out at the same rate. So now we had, and Einstein saying, look, this is weird. These quantum particles of which we're made up are weird. Yes, good point, Amanda. And it's just, he's saying, I'm not saying Professor Young is wrong. No, I've done his experiment many times, and it is a wave. Yeah, it seems to be a wave sometimes and a particle sometimes. That is really weird. And really, there was genuine scientific amazement. And believe me, today, scientists are just as amazed about quantum physics. But, oh, that's back to entanglement. I'll finish off superposition first. So what we worked out, what happened was we got to the sophistication where we could send 1 particle of light at a time through the slit. So before, when we were doing a ray of light, there were literally millions and millions and millions of photons going through. So here we sent 1. And so we were sending 1 at a time. So we expected to see, well, we didn't know what we expected, to probably see a clump pattern emerge, but it still was an interference pattern. So what the scientists of the day needed to do was they put a camera specifically on the slit to watch the particle go through and find out what was happening. And then please listen to this, because this is the amazing thing that happened. When there was, and it's called the observer effect, and we still don't know what's really going on. When we had a camera on the slit and we were looking at the particle going through, all of a sudden, the interference at the back went to a clump. So it's as if nature wouldn't allow us to find out what was going on. And what we realized is that before it's being observed, and that's a bad word, as we'll have a few questions and answers on this, I'm sure. But if the particle is observed, it becomes an actual particle, whereas before it shows, displays wave-like habits. It's like a wave, and then it's like a particle if it's observed. So this is a thing called wave-particle duality. Did one particle like go through following and get recorded as a pattern? Yes. Thank you, Amanda. That's a very insightful question. They went through 1 at a time, and as long as we're not measuring it or observing it, as long as we leave it alone, like Professor Young did, as long as we leave it alone, it will produce a interference pattern, 1 particle. So it's as if that particle is somehow reaching the double slit, splitting into 2, going through, and then interfering with itself. Yeah, it's the wavelength error which shows whether it's a wave or a particle. But the important thing, Amanda, what's that a good question there about time? Time is involved with it, but as soon as you observe or measure it, it collapses. And please write this down. This is the important phrase. It's the collapse of the wave function. And we don't know when, and we don't know what collapses it. But the important thing is this. Before we observe it, it's in a state of wave-particle duality. It shows wave properties and it shows particle-like properties. So it's actually in what we now call a superposition. So it's like it can be in many, many states at once. Which is weird. And also, how does it know when it's being watched or observed? Do other subatomic particles other than, oh, that's another great question, Amanda. And the answer is every single subatomic particle behaves like that. And some better than others, which is why we're trying to find the subatomic particles that we can manipulate more easily and consistently. But yes, and I don't know whether you guys are aware of the experiment in, oh, I've got to answer Ara's question there. It's, oh God, I've got what I was saying. It's, yeah, when you observe any subatomic particle, and we're finding what's called the subatomic particle zoo, or the quantum particle zoo. In CERN, there is a big hadron collider, the Large Hadron Collider, which is, thank you, Aditi, for the link, which is smashing protons into each other, and we're finding more quantum particles as we go. Now, before I move on, I want to answer a great question by Ara, which is, oh, I can't find it now, but it's basically, can we do with organisms? And funnily enough, I don't know how many of you know about this. I don't know how many of you heard about well, let me answer your question first, and then we'll go over these questions again. But when you're talking about an organism, funnily enough, there's a group only a week ago, I did a post on my channel that basically it said that it entangled one of the smallest organisms that we know of, which is called a tardigrade. Please write this down, tardigrade, T-A-R-D-I-G-R-A-D-E. They're an amazing small multi-celled animal, that we do call it an animal, and it can survive extreme cold, extreme heat. But the point is, they, in a way, they quantum entangled it with a qubit. It's not totally entangled, so there's still a bit up for discussion, but it shows that that's where we're going, and we're going to make more and more discoveries, no doubt. Oh yeah, but yes, they are, Amanda. So subatomic particles are listed like the periodic table. There's a thing called please write this down, the Standard Model. Now it's awful that it's got such a boring name, because it's the greatest breakthrough we've ever had, and the Standard Model goes into electrons, leptons, muons, taions, fermions, hadrons. It covers the lot, and neutrinos, and that's very interesting. So it is a periodic table, if you like. And now so there's superposition. So all you need to know is that we still don't understand, but quantum particles can be in many states at once. And that is the key to everything. So whereas we've got anything macroscopic can only can only be on or off. A light can be on or off, hot or cold. But at the quantum level, we can have something that we never see in the macro level, but we can have a wave particle duality where the quantum particle is in many different states, and we can reference to those states. And I'll explain that more when we go to computation. As if that wasn't enough, we've also got this thing called entanglement. And that is, with quantum particles, you can entangle them. And it's just a case of, you know, putting them through a laser and through a BBO crystal, firing a laser in a BBO crystal, and you can get entangled particles. And you can then put one on the moon and one on Earth, rather like the teleportation. That was done through quantum entanglement. That's what basically did the teleportation through different, what we call Bell states. But what scientists find, and as I say, no wonder they were amazed, they found that if you entangled these particles, and one's on the moon and one's here, and these particles are so small, they don't have length, breadth, or depth. They have something we call spin. It's like angular momentum, but it actually isn't. It's not spinning like the Earth is. And I'll use the Earth analogy a bit later. But it's basically when you change the spin of the one on Earth, the one on the moon changes immediately. And nobody knows how that happens. Einstein even suggested it wasn't happening. He went up with a big, what's called the EPR paradox. He actually proved that it wasn't happening. He didn't like it because it contravened the general theory of relativity. Something was happening, some communication was faster than light. So again, it's very, very interesting. And let's go into that more in the questions and answers. Okay, so with quantum entanglement, it doesn't happen in the macroscopic world, but it does in the microscopic. Einstein famously called it spooky action at a distance. And as I say, he even at the beginning said it wasn't happening, but then an Irish professor called John Bell proved that it was, and that holds today. Something crazy is going on. And there's a great game that you can play. Please look that up. You can look up the CHSH game, and you can actually play it. It's dead easy to play. And it proves that when you use entangled particles, they somehow are the one entity. It really is like having a person who has a fully coordinated arm and leg, and the arm's in China and the leg is in Russia, and yet they act as one. So it is amazing, and we don't understand it. And the important thing to understand, and this is a quantum spin, but here it's impossible to know the location of a subatomic particle until you measure it. So when it's in superposition, you can't say it's here or there. It's like, if you look at the classical world, you've got the Earth. Yeah, well, Amanda's saying maybe it's part of the oneness of our consciousness, source, God, whatever you want to call it. And the answer is we don't know. So I'm not going to say you're wrong, because science doesn't know what's happening. We can't explain it at the moment. And and consciousness seems to be involved in some way. But I will say straight away that it's not the scientific thought. Yeah, well, that's true. It's got a valid question in quantum physics. I think it's reasonable to say, oh, excuse me. Yeah, God is just a word, isn't it? I think it's reasonable to say that when we don't understand what's going on, let's not start saying other people are wrong. Excuse me. But there's one thing I wanted to mention here just before we go, because it's all tied into the Heisenberg uncertainty principle. And that states, and please write this down, with the Heisenberg uncertainty principle, which is the basis of superposition and everything, it says that we fundamentally cannot know the location and the momentum of a quantum particle. We can't know it. It's in this superposition. The more we know where it is, the less we know its momentum. And that's so important. Okay, we're going to take a 5-minute break now, and then I'm going to talk very briefly about the computation side of it. So it's 6:51. Let's get together at 6:56. I'll see you soon. Oh my God. Thank you, Joe. And we're just coming to the second session though, so that's not the actual end of it all. But, you know, if anyone has to leave, obviously, one can. Thank you, Ara. And let's see what time it is now. We've got a minute to go, and then I'll just ask a few questions for the quiz.
It's amazing how when you say quiz, one's heart still patters.
Yeah.
However many decades it has been since I've had to take a quiz.
Yes, I know exactly what you mean. One thinking, oh no. But look, okay, so it's 6:56. So let me just see if we can all get back in. Or if we can just say hello in the chat if you're there. Thank you, Aditi. And Ahira, thank you. Okay, I'll just, let me just ask a couple of quick questions. It's not an involved quiz today because I think we're going to run out of time as it is. But this is an important question. These questions are from my intermediate quantum computing course from New York. So it'll be good if you can get this. So the first question is, Heisenberg's uncertainty principle states that for a quantum particle, we are not allowed to know the location and what else? So just write it in the chat, and I can give you, oh, thank you, Anne. Yes, momentum. Thank you, Amanda. Yes, it's we're not allowed to know that. And if you just stop and think about what that means, it's really crazy. We can't know where it is. And it's not because we don't have the technology. As I say, it's like nature's not allowing us, but okay, let me ask another quick one. Next. When a quantum particle is observed, the following happens. A, it is suspended in space-time. B, it becomes a mini black hole. C, its trajectory speed is doubled. D, it collapses the probability wave function. And E, it becomes quantum entangled. Thank you, Ara. Yes, indeed, it is D. Thank you, Anne. Yeah, so wonderful there. I think you're all getting it. Let me move on to the second session, and then we can come back to any questions you may have. But it would be good to just touch on some of these points about, okay, it's weird. We accept it's weird, but that doesn't mean it can do computations. So I'm going to talk a little bit how it does it, and it's all down to superposition and entanglement. Now, the object you see on the right is a very famous object. So please write this down, the Bloch sphere. B-L-O-C-H sphere, S-P-H-E-R-E. The Bloch sphere is basically how we do all of its calculations, because we move around the surface of the Bloch sphere. And the Richard Feynman, who is attributed as being the original person, only in the mid-80s, not that long ago, he said, look, we don't understand quantum physics. We probably never will, but we can use it. Why can't we know? We haven't worked out yet, or too complex beyond our computing comprehension. Thank you, Amanda. Well, that's a difficult question to answer because obviously there could be something that we're not quite grasping. That's always the case in anything. But my answer to you today is that we're not being allowed to know. It's not the fact that our brains can't compute it, although it may be, obviously, but it doesn't seem to be that. It's not the equipment we have. It seems to be like we're not allowed. Nature, thank you, Amanda, nature doesn't allow us to know this information. And when we try and find out, it collapses. So it's in this superposition. We want to know more about it. But when we look at it, boom, it's not in superposition anymore. Instantly, it is in it becomes a particle. And the pattern literally changes the pattern at the back from an interference pattern to a clump pattern. So it's unbelievable. But the important thing is, in classical computers, they can only be on and off, 1 or 0. And look at the amazing things we can do, even with that. And I have my own little, I'm not sure whether you've seen it, Anne, but my own analogy of what that means and how it, you know, it's, I did this presentation for UWA and it was quite well received. It shows how much better a quantum computer is in theory. Oh, right, thanks, Sam. Okay, so only when it is of good need and purpose. Now this can become a lot of around the barbecue chat. Yeah, definitely. So what basically Richard Feynman, the guy who said we should be able to build a quantum computer, he was saying we can use linear algebra to work out the different phases and states of superposition. We can manipulate the superposition, if you like, without collapsing it. As soon as we do this through microwave pulses. So what I'm going to talk about is, one, what's physically happening. Like in a classical computer, there's a physical voltage either going through a transistor, it's either going through it or it isn't, which means it's on or off. In the quantum computing world, what we do is with microwave pulses, we can create superpositions which are different. And then we can manipulate the microwave pulse. So we can make it more intense, we can make it longer, and that will change the superposition. And we can, every time we send a pulse, what we're doing is putting it through a gate, a quantum gate. And that quantum gate is just a linear matrix. So it might sound a bit confusing now, but you'll be able to see the physical side of it, the algebraic side of it, and then the quantum computing side of it, which is basically microwave pulses, linear algebra, and quantum algorithms. That's those 3 different stages. So, okay. Before I get onto that, I do want to say how weird. Now, when you're around a barbecue discussing quantum computers, you can say how weird they are. Like I say here, quantum physics is weird. So it follows that quantum computers are weird. You cannot, a quantum computer cannot give you the result. And I equate this to, like, if you've got a calculator like the one behind me, I could say to you, hey, look, I've got this new calculator. It can multiply everything. It can do differentiation, integration. It can do the most complex mathematical equations ever conceived by mankind. The only problem is when I show it to you, it always says 1 or 0. Thanks, Arrow. Oh, no, 53 qubits, actually bigger than that. It's now, IBM's up to about 240 qubits. 53 qubits is what gave us quantum supremacy. I'll get to that a bit later. So yeah, honestly, isn't that crazy? It's like, and this is what happens to a qubit when you manipulate it by quantum gates. You can't look at, you can't measure it. You can't get the result, because if you do, it will collapse, and it collapses to 0 or 1 with almost equal probability, depending where you are on the block sphere. And that's so important, what I've just said there. So when it collapses, we live in a probabilistic universe. Einstein didn't like this. He wanted it to be deterministic. If you do this, then this happens. But we don't live, well, according to some of the interpretations, there's one called the Copenhagen, and you've also got the many worlds interpretation. But and so these are our interpretations. Amanda's asking, I hope the banks won't start using quantum computers. The banks are using it right now. Let me assure you, there's a lot going on in the background, especially in the finance sector. I'm involved personally with that. But yeah, it's when you measure it, you can't look at the answer. I love it because it's so stupid. And now, obviously, there is a way around that. Yeah, Bayesian is, yes, there is. Cubism, Ara has just mentioned, there's a number of interpretations of trying to explain quantum physics. And you've got cubism, the Copenhagen, the pilot wave. So there's the many worlds, there's a number of them. And cubism is a very interesting one. But we're not going to get onto that today. So again, I'm just saying how amazing it is that we can't know the answer. Also, it can't give you a result. It gives you what is most probably the right answer. So it's amazing. A quantum computer cannot copy and paste. There's a thing called the no cloning theorem, and that's very much involved with teleportation. And if someone could mute themselves, I'm not sure who it is. There's a bit of noise coming through. I think it's Joanne, but that's okay now. Yeah. So, you know, you can't copy and paste, whereas that's the major things that happens in a classical computer. You just say, whatever's in that transistor, put the same on and off in another one. So it's amazing. And qubits are still only working in milliseconds before they collapse. The problem is, and this is a good thing to remember, is that remember what we're doing is trying to manipulate a superposition. But as we've seen before, by us trying to measure it, it will collapse. Any little bit of radiation, like heat, will collapse the wave function. So it's very, very, very delicate. And all the different types of quantum computers, what they try to achieve is they try to isolate it, the subatomic particle, and keep it in superposition. And that's very, very difficult because it interacts with everything. And we don't want it to do that. I won't go into P versus NP, but it just means quantum computers are going to do calculations we never thought possible. So let me go on to the next one. I'm going to have to go through this rather quickly, but when we talk in the classical world, let's imagine we have the Earth. So the Earth, oh, that's okay, Joanne. The Earth is, this is the Earth as a bit, and then I'll show you the Earth as a qubit. So I say to the younger people I work with, I say, I lecture to, imagine getting 2 A4 sheets of paper, running up to the North Pole and sticking one on the North Pole and writing a 0 on that one, and then going to the South Pole and sticking the A4 sheet of paper on the South Pole, and you put a 1 on that. That is how every computer works, including the one that does 200 quadrillion operations a second. Sorry about that. You can only have 2 A4 sheets of paper, and they can only have a 1 or a 0. Now, and look at the amazing things we can do with that. But the good thing about this is that it'll always have a 1 or 0 on it. When we turn the A4 paper over, it will have a value of, it'll always be 0 at the North Pole and 1 at the South Pole. So it's very, very deterministic. And that's how our computers work. They never make mistakes. You know what I mean? So, but a quantum computer can cover every inch on the Earth. You can have a different state. It won't be 1, it won't be 0, it will be something in between. Now, that is amazing. So I actually worked out how many A4 sheets of paper you would take to cover the entire Earth, and the answer is 8.2 trillion. So we could literally, now we can't because we haven't got the microwave pulses down to that control, but theoretically there are an infinite number of superpositions that we can reference to. But when we look at them, and when we look at them, we can't turn the page over, because as soon as we do that, we're collapsing the wave function. So we can't look at the answer, but we can know the location, which I call it latitude and longitude. These are what we call, in reality, complex amplitudes. And, you know, I really have to rush this, so I can't go through all of that. But all you need to know, and this is very important, the location of the A4 piece of paper is very important, because the nearer it is to the North Pole, the more chances when you look at it, when you measure it, it will go to 0. And the nearer it is to the South Pole, when you look at it, it will go to 1. Now, you may not think that's important, but let me tell you, that is everything. That is how quantum computers can actually come up with a solution. It's called quantum tomography. It's I'm doing an analogy of quantum tomography, which allows us to know the answer without looking at it, without measuring it. And this is where, as if that's not enough, that we can manipulate the qubit into whatever it was, 8.2 trillion different states. Not only that, but we can link the Earths together, which we cannot do in the classical world. And because through entanglement, how do you do the mapping of a possible location of a qubit? Because of those, that's a great question, Amanda. Amanda's asking, how do we let me just make this bigger. How do we map the location of a qubit? And we do that by those latitudes and longitudes, the complex amplitudes. So that means the probability that it's 0 and the probability that it's going to go to 1. But don't worry about that now. The point thing is we can individually map to all of these strange locations. And then we can entangle them. Now let me show you the effect that has. Should an alien come down and say, I've got a number here, I want you to tell me what that number is in one go. It's a 6-digit binary number. So it could be 110011. And you have to tell me what the answer is. Obviously, this is just a bit of a joke. But with a classical computer, the only way you can do that is by what's called concatenation. You can place bits like an abacus. And I like to explain it that way. You can get photocopies of the Earth and place them as you would in an abacus, and you would check each one individually. And you would say, is it a 0 or a 1? Is the one on the right, the one on the second to the right, is that a 0 or 1? And there's ways you would work it out. It's impossible to do it in one go. Yes, Ara, I'm just about to, you've just preempted the next slide. But a quantum computer, because it's entangled, it can check out every number at once. And a good way to think of this, it's like a maze. When you have a classical computer, it literally tries one path at a time, whereas a quantum computer tries every path at the time, and it has a way of finding out which was the right path. You know, so it goes through them all. The one that comes at the end is the right path. And that might be the one of least resistance. Yeah, we don't need to go into that. And again, quantum computers can only say what the answer probably is. Now, people think, isn't it able to find the best path, but may not necessarily tell you it's the right path? No, it's programmed to tell you what's called the ground state. So if we're trying to find a phone number in a, oh, thank you. Yes, they were Lorraine from Zimbabwe. Thank you for the session. Look forward to talking to you soon. Yeah, it's, so the ground state is what it will tend to get to. And you make the ground state the solution, but that's quite an involved question, Aditi. But the important thing is, yeah, you can set up the what's called the, oh, I can't remember what to call them. Oh, never mind, it'll come to me. But you can set up the parameters and then it will actually answer that. But if I can just make this last point, we're doing great for time. We're going to have 10 minutes left, and I think that's important for questions and answers. So we've touched on things here. If I asked you, if you threw 2 dice, what are the chances of getting 2 4s? We can work that out using mathematics. But there's another way of working it out, and that is throwing the dice a million times. And this is a thing called the Monte Carlo. It's it's a very, very important, it's called the Monte Carlo simulation, which sort of says, instead of doing the very, very difficult mathematical calculations, we can actually, with computers, we can run the algorithm, we can throw the dice many, many, many times, and then the answer will give us the location on the Earth of the on the quantum Earth. And that's not bad timing. And that will, so that's the way we measure it. And I've been very unfair to you all because I've gone very quickly. But here, by knowing the complex amplitudes, we can, by running the quantum algorithm a million times, it will come up with so many ones and so many zeros. And that will show us, and this, Aditi, answers your question. This, then, the amount of zeros and ones we get, it will relate it. Thank you, Amanda. It will show us the location, and from that we can work out the complex amplitudes and the result without even looking at it. Wow. Okay, thank you, Aditi. So look, that's the end of the presentation, you know, and it's been great. So I thank you all. There've been a lot of very good questions. Now let me open it to the floor and ask questions on anything you wish. You can unmute yourselves if you wish, rather than texting all the time. It's probably better. So I'm unmuting you all.
Thank you, Eamon.
Pleasure.
So I was quite proud. I was catching some of what you had done in the beginning, right? Because I've heard that many times before, and it's only starting to sink in. And then gone. So the Monte Carlo simulation.
Yes, that's important.
So that's running the algorithm, or running what you're doing many times.
Yes.
So that you don't have to try to observe something.
Yes, let me give you yes, you've got it absolutely right. The Monte Carlo is used in mathematics and in business all the time.
Mm-hmm.
Stock portfolio optimization is a big one. And they use the quantum Monte Carlo. What they're saying is, if you've got an option and there are various factors that are going to affect the price of that option, you can either try and work out with complex formulas, or you can run a Monte Carlo simulation. And that's what's happening now. Every single bank, financier in the finance sector will run a Monte Carlo simulation. And the example that I gave you there was rolling a dice. And that's probably a bad example because that's so easy to work out. But you imagine, and what it was actually done with was a game of solitaire. So this very clever mathematician, oh yeah, thank you, Aditi, yeah. This very clever mathematician who was in hospital, and he was playing solitaire, and what he thought was, I wonder what my chances of winning are. And he actually started doing the maths. Now you can imagine how complex it is, you know, to do, if this square is 3, do you go there, or do you go there, la-di-da-di-da. Very, very complex. And he said, hold on a minute, what if and we're talking the 1940s here. And he had a friend who was working with the ENIAC, the first supercomputer ever built. And he said, could you run this game a million times? And they said, yeah, sure. It'll take about a week, but we can do it. And that's what happened. And now, obviously, computers are faster and faster. But classical Monte Carlo simply can't handle it. Aditi saying she's doing one in the health industry, which is, you know, fantastic. It's used everywhere. And what it means is without, you know, you don't have to work to predict the future. You don't have to do advanced maths. You can run a simulation.
So is there a classical Monte Carlo and a quantum Monte Carlo?
Great question. There is a classical one, and there are many developers in WA as well, I might add. There are many developers who are developing a quantum Monte Carlo as we speak. And there are people in the States who assure me, I talk to them all the time. In fact, I'm doing a talk with a Washington, DC group, which is very up with quantum in finance. And they say they'll have a quantum Monte Carlo available within 6 months. Not sure I believe them, but there's a race on, believe me, because you've got so many people in so many different industries using the classical Monte Carlo. And, you know, there's only, like if we were using stock portfolio optimization, you know, there's only so many stocks you can do at once. You can only project it so long. And it literally is taking hours and hours and hours to do it. So the quantum Monte Carlo is going to be a world seller, and everybody's on top of it. Great question, and thank you for that. And there's something wrong, which is so frustrating with my, I've fixed it now, even though it's a bit of a nuisance. Speaking of biology, thanks, Ara. I don't know whether you just asked this. Because observation influences particle, if that can somehow be measured, can quantum computers calculate consciousness? Would it depend with the amount of calculations? I don't think quantum computers are going to solve that problem, because they are a bit like a computer. You have to feed things into them. But certainly tests and experiments, the likes of which are happening all the time. There's an experiment that was only done a year ago in the University of Edinburgh that proves the universe is not objective, which means that my universe, something could be collapsed in my universe, but not collapsed in your universe. It comes, please write this down. It comes from a thing called Wigner's friend, W-I-G-N-E-R, Wigner's friend. That's a concept that he's saying if somebody collapses a wave function, is it collapsed for everybody? Okay, but let me just, Aditi's asked a great question. So the difference between classical and quantum would be running the simulation and getting results over time versus instantaneously. Much more than that, it would be more accurate. The risk would be less, but yeah, basically it is a huge speed up. That will certainly be the biggest, well, actually, I think they'll all be big, but
I think that question, I was asking it based on the Monte Carlo simulation, having it classically done versus quantum.
oh, absolutely. I was answering it with respect to the Monte Carlo. Yeah, because it's so involved. The classical Monte Carlo is horrendously slow, and you can only have so many operators. But progress on the quantum Monte Carlo is happening, and it will result in a huge speed up, and it will reduce the risk, and you'll be able to do huge stock portfolios. And I might add the same in medicine and things like that. Vaccines, I think it was Hira asking some questions about biology and medicine. So soon we'll have personalized medicine, because we all react, as we know, unfortunately, in these times, we all react differently. Our metabolisms act differently to different vaccines and medicines. And that's because of the different electron exchange, but we'll be able to simulate it on the fly. By the way, that's only when we have a pure computer and when we have many of them, many qubits. At the moment, IBM are talking about having 1,000 qubits at the end of next year. Ara, I don't know whether you're still there. You were mentioning 53 qubits. That was the sycamore that proved quantum advantage. But in actual fact, IBM, yes, yeah, IBM are now operating on a 240 qubit superconducting computer, and IBM, a fantastic presentation. I think it's on my channel. I definitely posted it, but IBM don't make things up, and they're not a Apple has always been a very out there company. Oh, we can do it, we're going to do this. IBM's always been very traditional and down the line and understated. And they're saying they're improving much faster. Their systems are developing much faster than they thought they would. And having a 1,000 still NISC, so it's not pure, but they're having a 1,000 qubit computer in a year, it will happen. But you can't just measure computers by the size of the qubits. Ara's asked the question, how long until we get 300 qubits? Is there a Moore's law? Oh, let me look at that again, because I'd like to see. How long until we get 300 qubits? Remember, it's 300 pure qubits. Is there a Moore's law for them? No, there isn't. If so, can we calculate the whole history of the universe? Yes, we can, theoretically. From the Big Bang, yes, that is one of the things I normally say, Ara, that we will be doing. We'll be simulating the Big Bang. Yeah, so NIST, thank you, Ara. So we're at NISC at the moment. So quantum developers around the world are writing these programs, knowing that, you know, they're making it error correction. Error correction's a big thing at the moment. Thank you, Aditi. Yeah, it is incredible. That's exactly what it is. And you know, we've had this 90-minute presentation, but we've still hardly touched on the sort of thing it's going to do. Anne knows this, but I always say, when people ask me what are quantum computers going to solve, the first thing I say is the the unknown unknown. And most physicists will say that, because okay, we know it's going to give us 100% cryptography. We know it's going to do quantum teleportation, maybe up to atomic teleportation. I don't want to mislead you that it's around the corner, because it certainly isn't. Thanks, Anne. Lovely to see you again, as always, and we'll talk soon. So I don't want to mislead you to think that these simulations are going to happen in the next year or two. They will probably be 30 or 40 years away. But it is the unknown unknown that's going to be, there's going to be some application we haven't even thought of yet. And it will change everything. Like Jeff Bezos said, something's going to change. We don't even know what it is. But to talk about what we know it will do, so the known unknown, we know that it will change the finance industry forever. It will allow 100% unhackable code. That will change so many things you won't even understand it's changing it. Quantum networks, so the quantum cloud will allow telemetry-like properties. So we've already got drones that are quantum entangled. So they're doing things at exactly the same time under certain conditions. We can quantum entangle many subatomic particles at once now. And as Ara asked, we're sort of not far away. I'm not going to say, there's a lot of conjecture whether this group, I think they were in Holland, they say they quantum entangled this tardigrade, that by affecting the qubit, it affected the tardigrade. There's a lot of skepticism about that, but it doesn't matter. It's the first step to us entangling organisms. Now, you can work out what does that mean. You know, it is incredible. It means we could be walking on Mars simulated exactly at exactly the same time, doing things on Mars whilst doing the same thing here. At the moment now, there's a 8-minute delay or 6 minutes, something like that, with everything we do, which is obviously very frustrating. These things, distance will not be an issue. And there's one other thing I'd like to say. With quantum entanglement, distance doesn't matter. But there's a few experiments, including the delayed choice quantum eraser, that show that time is irrelevant. So you can entangle things over time. That means you could write a code or an encryption on atoms that don't exist yet. Because time plays a part in all of this. We don't understand quite how at the moment, but the delayed choice showed us that effectively events that have already occurred can be altered in the quantum realm. So it's good stuff. Yeah, hi, Joe. Look, thank you very much, Joe. Lovely talking to you and seeing you again. Thank you, Aditi. Yeah, we've had a good long session. I hope you've all enjoyed it, and I look forward to talking to you all soon.